Hey there, and welcome. If you're getting ready for an exam on angle and pulse modulation, you are in exactly the right place. We're going to break this all down step by step. All right, so here's our game plan for today. Think of it as our roadmap. We'll start with the big picture, the why. Then we'll tackle the two major ways to do this, and wrap it all up with a review so you can walk into that exam feeling confident. So let's start with a really simple question. Have you ever wondered how your car radio can sound so crystal clear even when there's a thunderstorm raging outside? Well, to get that, we first have to understand the problem it solves. Think about an old school AM radio station. On a nice sunny day, it's fine. But the second a storm rolls in, it's all static, right? That's because all that electrical noise in the air directly messes with the amplitude of the radio wave. That's just a fancy word for its height or its strength. And here's the kicker. AM radio encodes all its information, the music, the voice, right there in those changes in strength. So when noise changes the strength, it ruins the sound. And this right here shows the solution perfectly. On the left, you can see what happens in an AM system. That original signal gets totally mangled by noise. It's a mess. But now, look at the diagrams on the right. See that? That's what happens when you use a totally different method, one that just ignores any changes in amplitude. The output? It's clean, it's stable. This, my friends, is the magic of frequency modulation, or what we all know as FM. That's the secret to clear radio in a storm. Okay, so that brings us to our first major concept, understanding angle modulation. This is the first big family of these more advanced techniques. And like we just saw, it's the secret sauce behind that high-quality FM radio we all know and love. So what exactly is frequency modulation, or FM? Honestly, the idea is pretty brilliant. Instead of messing with the wave's strength, its amplitude, the part that gets all distorted by noise, we change its frequency. That's it. We just change how fast the wave wiggles up and down to encode the sound. And that one simple change makes all the difference. Think about it. By putting all the important information in those frequency shifts, the FM receiver in your car can basically just turn a deaf ear to any random spikes in power from lightning or your engine. It just doesn't care about them. And that is precisely why your FM station sounds so much cleaner than that old crackly AM station. This diagram here really lets us see it in action. So that top wave, labeled A, that's our sound, the music, the voice we want to send. We call that the modulating signal. It's modulating or changing the wave below it, the carrier wave, which is just a steady, predictable wave that carries our info. Now look closely. When the sound wave A goes up to a peak, see how the carrier wave's wiggles get all squeezed together? That's a higher frequency. And when the sound wave hits a low point, a trough, the carrier wave stretches out. That's a lower frequency. But here's the key thing to notice. The height of that bottom wave never, ever changes. All the information is in that squeeze and stretch. Now, FM has a very close relative called phase modulation, or PM. It's another type of angle modulation, but the idea here is, instead of changing the frequency, we shift the phase of the carrier wave. You can just think of it like we're nudging the wave a little bit forward or backward in time to encode the information. Now, these two are super closely related. In fact, changing a wave's phase automatically changes its frequency for a split second, and the other way around. So for your exam, here is the one key difference you need to nail down. What property are we directly controlling? If it's the frequency, it's FM. If it's the phase, it's PM. Simple as that. And here you can see them side by side. The resulting PM and FM waves. Yeah, they look a little different, but that's not the main point. The big takeaway here is that they're both types of angle modulation. They both hide the information in the timing or frequency of the wave, not its height, and that's what gives them that awesome resistance to noise. All right, so we've totally nailed how angle modulation protects a continuous wave. Now, let's just throw that whole idea out the window and switch gears to a completely different strategy. This is called pulse modulation. The question here is, what if we don't send a continuous wave at all? What if we just send a bunch of short little blips or pulses? Okay, so for this to work, we have to start with a foundational idea called sampling. Imagine you want to describe a flowing river, but you can only send a series of still photos. Sampling is like that. We take thousands of super fast snapshots of the original sound wave, measuring its height, its amplitude at these perfectly regular intervals. And the cool thing is, if you take enough of those snapshots, you can put them back together and perfectly recreate the original flowing sound wave. The most straightforward way to do this is called pulse amplitude modulation, or PAM. It's super direct. For every one of those snapshots we take, we create a pulse, and the height of that pulse perfectly matches the height of the original wave at that exact instant. And this diagram shows you exactly what's happening. The top wave is our original sound. The bottom signal, C, is what we get. It kind of looks like a picket fence, right? And the height of each picket matches the original wave. It's a really simple translation, but do you see the problem here? Where is the information stored? It's in the height of the pulses. That means it's right back to being vulnerable to the exact same kind of noise that messes up AM radio. So how do we get around PAM's big weakness? Well, we use something called pulse time modulation, or PTM. And this idea is really clever. We just make all the pulses the exact same height, so amplitude doesn't matter anymore. And instead, we hide the information in their timing. We can do this in two ways. We can vary how wide each pulse is, which is called pulse duration modulation, or we can vary its exact position in time, which is pulse position modulation. Now that the pulse height is totally irrelevant, the signal is way more resistant to noise. Okay, let's move on to what is maybe the single most important concept in all of modern communications. We've gone from smooth, continuous waves to these little discrete pulses. Now we're going to take the final revolutionary leap and turn those analog pulses into something else entirely, something almost invincible: digital code. This is pulse code modulation, or PCM. Okay, so after we sample our wave, we've got all these pulses, but their heights could be anything: 1.2 volts, 1.21 volts, 1.211 volts. It's messy. The first step to going digital is a process called quantization. Think of it like rounding numbers. We take the height of each pulse and we just snap it to the nearest predefined level. So instead of infinite possibilities, the height of each sample now has to be one of, say, 16 specific values or 256 specific values. We're forcing it to be neat and tidy. And this slide just shows that process beautifully. That smooth original wave is being forced into this stair-step shape. In view C, it's only using 5 levels, so it's a kind of clunky approximation. But look at view D. It's using 10 levels, and you can see it's a much closer fit. The takeaway is simple. More steps means better quality sound. And now for the final, absolutely game-changing step: pulse code modulation, or PCM. We take every single one of those quantized stair-step levels and we replace it. We don't represent it with a voltage or a height anymore. We replace it with something totally abstract, a unique binary code. The lowest level might become 0000. The next step up is 0001, and so on. We are no longer sending a physical representation of the sound. We are sending pure, abstract information. And this slide right here shows the incredible payoff. Look at the table and find the decimal value 13. In the old analog world, we'd have to send a very specific, very fragile voltage to represent that. But now, we represent it as the tough, sturdy digital code 1101. And that code is then sent out as a simple series of pulses. Pulse, pulse, no pulse, pulse. See that on the right? It's just on, off, on. It is a fundamentally different and way more reliable way to send information. And here is the ultimate so what. It is incredibly, ridiculously easy for a receiver to tell the difference between a pulse being there, a 1, and a pulse not being there, a 0. It can do that even if the signal is super noisy and weak. As long as the receiver can make that one simple decision, is it on or off, it can perfectly, flawlessly rebuild the original code. This incredible immunity to noise is why PCM is the undisputed king of modern communication. It's in your phone, it's how you stream video, it's everywhere. All right, deep breath. We've covered a ton of ground. Now let's lock all that knowledge in with a super quick review and some practice questions. This is the stuff you absolutely need to have down cold for your test. So here are the heavy hitters we covered. Angle modulation, that's FM and PM, where we change timing to beat noise. Then pulse modulation, PAM, PDM, and PPM, where we use pulses instead of waves. And finally, the digital dream team, sampling, which is taking snapshots, quantization, which is rounding them off, and pulse code modulation, or PCM, which turns it all into bulletproof binary code. And to finish things off, here are some questions pulled right from the source material. My advice? Go ahead and pause this explainer for a minute and really see if you can answer them. If you can explain these concepts in your own words, you are going to be in fantastic shape for that test. Thanks so much for watching, and seriously, good luck.